idee van de 5K was dus dat je makkelijk
ja, maar dat was eenmalig. Ook goed teams die over 3 jaar beginnen hebben, dat is niks.
Dus we kunnen ook gewoon 2015 in elkaar komen. Maar dan ben je een lifecycle. Dus eenmalig. Nee, dat kan ook niet snappen. Ik zou denken, nu weer voor de 5 jaar. Blijft niet door.
Okay. It works. It works. Last year we presented Alisa, our modeling language for cooperative agents, and I know that some of the people that are here today weren't present in the last year, so I just give a tiny overview on how Alisa work in general. So the basic idea is that we have a state machine for a single agent, and when a certain condition holds, like when the ball is found, we will transition from one state to another state. And within a state, we usually have a simple atomic behavior that is only a short piece of code that's achieving that the robot is driving to a certain point, for example, or to align for a certain goal or to shoot or so. So when we now have more than one robot, then we have also more than one state machine. And so the goal of coordinate agents is now how can we achieve that agents transition from one state to another synchronously, and how do we assign the robots to the state machines. And therefore we first group the state machines to a plan, so state machines that have some connections, like this example, it could be a gameplay plan where we have some attackers, so let's say one attacker, 0 to infinitely many defenders, and one goal. Then each plan has a precondition and a runtime condition that has to be valid in order to enter a plan, respectively in order to stay within the plan, and the utility function. So the utility function is the thing that we use to determine which agent is executing which task. So this is a function where you can just query for a specific assignment, and a high value means that that assignment is a good assignment to achieve the task, and a low value is a bad assignment. So for example, the robot that is attacking should be close to the ball. This might be a good assignment, for example. Yeah. Then 2 years ago, the problem here we get is that we had a lot of states, because for each standard situation, especially when, let's say, there is a throw-in that's close to the penalty area, then we always had to implement some exceptions so that we keep the rules. And in order to make this easier, we added variable values that allow us to be some kind of parameterization for behavior, so that we cannot just say pass to 0.00, but we can say pass to a point that we can determine somehow else. So in our case, we usually use a constraint problem that describes the goal which we want to pass to. Yeah. So this is somehow the wrap up of the last year, what we presented there. And now I want to give you some motivation for what we did last year, and so after the workshop and till today, more or less. So I want to start with the motivation, which is basically why we need coordination or agreement on mutual goals. So when you see this picture, both animals want to eat the hay, and and initially both move in contrary directions, so none of both is able to eat the hay. So, and the motivation is obviously, the solution is just eat first one of the hay and then the other one. And to model this in ALISA, there are several ways. So it's a language, and in each computer language you have several ways to model the problem. So the first, and I would say most straightforward and easiest one, is just to have a state machine with a state that says, okay, eat first the left hay and afterwards the right one when it's empty. So the problem with that is you have 4 states for two different blocks of hay. And another problem is that we cannot ensure that both agents agree on which time when the hay is empty. So maybe we have difference of observation on our environment, and then we can have a conflict. So therefore we could add, was one way, a synchronization point in ALISA. But this is usually not what we want to do, because we have other ways. For example, we could do it by making according assignment. So moving the problem to the assignment problem that's computed by the utility function. And there we have one task that says eat the first hay and eat the second hay for the next task. And we will already have the half amount of states, because we only have one state per block of hay. But the thing we would like to enforce in general is what I already mentioned, as the plan variables, so that we can say we have only one state, no matter how many hay we have, and then we determine a variable x that first leads us to the first hay, and when we are finished with that one, we go to the next one. Yeah, but what's the problem here is, first of all, we don't have any conflict resolution built in ALISA. So ALISA has conflict resolution for the synchronization and for the task assignment problem, but not for the not yet for the variables. Another point is also that even when that doesn't fit that much to the example, the whole team always has to do the same decision, currently at least. So if assuming that the internal model of our robots is similar, all robots will more or less have the same solution for the constraint problem. And yeah, but in sometimes we want to have one agent that says, okay, this robot becomes attacker and this robot is doing something else. Might happen. Then currently we only supported numeric data types, so especially we're not able to make lists of goals. And finally, we didn't support any persistence. So usually in each iteration of a control loop, we computed everything from scratch again. Not from scratch, but we computed again. Yeah, so overall, we wanted to do some agreement for variable values. What we already had before is the formalism that allows you to determine the variable values is completely exchangeable. So you don't necessarily need to determine the variables by a constraint satisfaction problem. You could also do some, I don't know, we have some people who are working on ASP, for example, currently. Yeah, and therefore, but what I want to talk about now is how we want to resolve the conflict of the variables. Yeah, that would be develop case, Carpe Noctem consensus engine, which is basically a tuple space with replication, and that especially supports communication when we have unreliable situations like in RoboCup where a lot of packets get lost. We also know that from the theory of distributed systems, conflicts, we cannot completely avoid conflicts in general. So either we would have to need more time to ensure that we have agreement, or we could do it like this, that we allow conflicts for a certain amount of time, but they have to be resolved after some time. Yeah, and of course, complexity, and as if we want more complex data types and consistency for the variables. Yeah, so the basic idea is that for each variable we have a proposal from each robot. So when we want to determine which hay we eat first, then each robot can make a proposal, and then we can decide on based on the proposal that arrived at our robot, how we want to decide. Then of course, if a robot is disconnected, that whole thing should still work. And then we will maybe have an outdated variable proposal. Yeah, so therefore we need basically three components. First is the consistency strategy, so it's something that ensures that a replicated proposal is consistent replicated. Like, let's say I now set a variable proposal and I want to achieve that it's at least in 1 second is replicated, for example. Then we need some acceptance strategies, which basically answers the questions when we overtake a received proposal as our own proposal. And finally, a value decision strategy that allows us to determine the current variable value. So this can maybe, will be later on the slides, a minority decision, so that we have some fault tolerance in our system. Consistency is very easy, so you can basically choose between 4 levels. So you can just say about this variable we do not want to communicate at all because it's not interesting for the other robots, it's only for one robot. Then we can have something like fire and forget, where we just send a message and we don't care whether it arrives or not. That can be the case, for example, when you pass a ball, when you already shot the ball, when you wait until the resend messages arrive, then the situation will be completely different. The next level is ensures that at least at each robot arrives the message that we change the variable value. So if we need assurance that a variable value is from the robot that sets the variable value is does arrive at all robots. And finally, if you also want to ensure that all the proposals from the other robots arrive at all others, then we will need a 3-way handshake. So this is straightforward, but how a lot of different technologies does it currently right now. Then the acceptance strategy is nothing else than ordering all the value proposals by a certain attribute of the variable value. For example, the easiest way might be to order it's not belief, it was the proposal by its Lampert time. So we add a Lampert timestamp, it's a logical timestamp to each variable that we send through the network. And then we can just say, okay, you only take variable proposals as your own proposal when they have a higher or lower variable timestamp. Yeah. And then finally, as I already said before, for deciding which variable value to choose, we could do a majority voting to ensure fault tolerance. We could say, okay, for a specific thing, like when we set a distributed mutex, we might be interested in having a full agreement so that all robots say, okay, I will not do this, so you can do it. Or maybe we only just take the most recent variable value. Then we would allow errors and conflicts within our decisions. Yeah, but it's faster, obviously. The first results which we did were only on the first 2 parts of this case stuff. And it's basically the latency, and on the next slide, the network delay for when we use faulty network connections. The interesting thing which we figured out is that middlewares like DDS have a very high latency when you start sending bigger network packets, because I guess that half a millisecond is a lot for just for delay. This does not include any network delay. It's only sending a message and receiving the message at the same, not at the same endpoint, but a different endpoint at the same robot. So only network stack to the lowest level and to the highest level again. Yeah. So our implementation is let's say, 3 times slower than having pure network socket with UDP multicast. And when we insert unreliable communication, then we can see that after 20 to 30% packet loss, standard TCP connection has horrible transmission times. So packets are sure to arrive in TCP, but for 30% you will already need 5 seconds on average that a package arrives at another endpoint. Yeah, a DDS is a bit faster, and our implementation is the fastest one. So this is the main reason for that is that we had an own model that determines when we resend a lost packet. Yeah, so this is a short version of how it works. So all I can provide in that short amount of time. So that's my talk. Any questions?
I have one question. In your timing diagram, the last one, I missed UDP. What about just send it